Hey everyone! So I want to start off by saying that this video is intended for students that have already taken and passed Algebra 1. If you haven't taken Algebra 1, I'm going to be using vocab words and talking about techniques that you haven't learned yet. So while this video is about an Algebra 1 topic, if you haven't already learned this topic, this video will not be enough to explain the topic. The intention of this video is to provide enough information to jog students' memory about how to solve a system of equations. If you have no idea what a system of equations is, this video won't give you enough background information to help you solve them. So this video will cover what is a system, and then we'll talk about solving systems of equations in two different ways, with the elimination method and with the substitution method. Let's start off by defining what a system of equations is. It's two or more equations with the same variables. For the purpose of this class, we will only ever look at a system of equations that contains two equations. So here's an example. We see two equations and they both have the same variables, x's and y's. This is an example of a system of equations. The more important question is, what does it mean to solve a system of equations? Because that's what this video is about, teaching you how to solve a system of equations. Solving a system means you find the x and y values that make both equations true. And the key word here is both. I would like to add that not every system of equations will use the variables x and y. There might be other variables used instead of x and y. So you just want to find the values of the variables that make both equations true. So let's talk a little bit more about what I mean by make both equations true. So the answer to this system above is x equals -6 and y equals 4. Oftentimes, solutions are written as an ordered pair. But why is this a solution? Why does that match the definition of what it means to solve a system? What it means is if I were to plug this x value and this y value back into either equation, it will make the equation true. So if we wanted to check that this was the correct answer, we could do so easily. So first I'm going to be checking in the first equation. There's the first equation again. If I replace x and y with these two solutions, the equation looks like that. And now we just want to make sure that this equation is true. So if I simplify the left-hand side of the equation, I want to make sure that it gives me -14. And it does. I typed this entire expression into my calculator and it gave me -14. So this solution, x equals -6 and y equals 4, worked for the first equation. But like I already said, one of the key words here is both. So just because this solution works for the first equation doesn't mean it's a solution to the system. We have to find a solution that works for both equations. So I would also want to double check that this solution worked for the second equation. I'm going to do that using the same method. There's the equation. I plug in the solutions for x and y, and then I simplify and make sure that the equation is true. I'm left with 6 equals 6, which is obviously true. So this answer works for both equations, the first and the second. So that's important to understand what it means to be a solution to a system. It means it's an x and y value that work when you plug them into both equations. So let's talk about how we would actually get this solution on our own. How do we solve a system of equations? My favorite method is the elimination method, and that's what I'm going to talk about first. So first of all, here's a question that we're going to answer using the elimination method. And this question is nice because our variables are already stacked. In order to use the elimination method, you want to have your x's on top of each other like they are here, and your y's on top of each other, and your constant terms on top of each other. So it's really nice when both equations are already written in standard form. Both of these equations are written in standard form, which means that our variables and our constants are already stacked. Sometimes you have to rearrange an equation to get the variables stacked. It's not that much of a problem, it just adds another step to this method. So since our variables are already stacked in this problem, my first step is going to be to create opposite coefficients on one of the variables, either on the x's or on the y's. So I normally like to look at the coefficients in front of the x's and look at the coefficients in front of the y's and ask myself what number is divisible by both 6 and 4, or what number is divisible by both 3 and 5. And there are multiple answers to this question, so there's multiple ways to proceed from here. The way that I want to keep going is by creating opposite coefficients on the y's. So to do that, I'm going to multiply the top equation by -3 and the bottom equation by 2. Why did I choose these numbers? If I multiply this by -3, it's going to give me a coefficient of -12. And if I multiply this by 2, it's going to give me a coefficient of +12. So I will have achieved the opposite coefficients that I wanted. Is this the only way to achieve opposite coefficients? No. Some of you may wanted to create opposite coefficients here. You can do that too. There's many different ways to do this, so long as you're creating opposite coefficients. So once I've decided what I'm multiplying each equation by, I have to make sure that I multiply correctly and that I keep the equation balanced. So if I'm multiplying the top equation by -3, I have to make sure that both sides of the equation get multiplied by -3 and that all of the terms get multiplied by -3. So after multiplying correctly, I should end up with this. You'll notice every single term has been multiplied by -3. It's a common mistake to not multiply all 3 terms by -3. The bottom equation is going to get multiplied by 2. That gives me this. Once again, all 3 terms were multiplied by 2. And you can see that we have achieved opposite coefficients in front of the y. That's awesome. That's what we wanted. You'll see in a second why that's so helpful. Now that we have achieved this, we're going to add up both of those equations. And it's nice that my variables are stacked. You can see what happens with the y's. They cancel because -12y plus 12y, those two terms are opposites and they'll cancel. So we're about to go from 2 equations that had 2 variables to 1 equation with 1. If we add up the x's, we get -9x, and if we add up the constant terms, we get 54, and then once again, these y terms canceled. So we're left with this equation, which is way better than what we started with, because there's only one variable, and we can solve it. So I would solve this equation, I'd divide both sides by -9, and I get x equals -6. So I know what one of my variables is equal to. We're halfway done with this problem. We still have to solve for y. Thankfully, once you have one variable, it's pretty easy to find the next. I'm going to take this variable that I now know, and I'm going to plug it in. I can either plug it into this original equation, or either of the equations after I manipulated them. It really doesn't matter. For this problem, I decided to take this equation. But now that we know what one of the variables is, we know what x is, we can plug that in. So I plugged in -6 for x. And now I'm left with one equation with one variable, and I can solve. So I added 30 to both sides of this equation, and then I divided by 4. I get y equals 4. So my final answer for this, written as a coordinate pair, would be -6, 4. And I'm not going to go through the process of checking this solution, or at least I'm not going to show you the process of checking this solution. It is always worth your time to take what answer you think is correct and plug it into both equations to make sure it works. So this was method number 1, the elimination method. I use this for every single system that I'm asked to solve, except for in one scenario. So here I'm about to talk about the one scenario in which I wouldn't use the elimination method, but rather I would use the substitution method. So if and only if one variable is already isolated, so already all by itself on one side of the equation, I use the substitution method in this scenario, right? If a variable is already isolated, and for everything else, I use elimination. So once more, I would only use the substitution method if you already have one variable isolated. So in this scenario, I'm going to show you the substitution method, and it's pretty easy because we already have this y all by itself. If you don't already have an isolated variable, I wouldn't recommend the substitution method because you can get a lot of ugly fractions that make it hard to solve by hand. All right, so we already know that y is equal to this expression, 7x plus 15, which means I can plug 7x plus 15 in for y. If they're equal, I can substitute them. That's where this method gets its name. So I'm going to rewrite this bottom equation, except instead of writing y, I'm going to substitute in 7x plus 15. So that's what I did down here. You can see that y does not appear any longer, but that it's been replaced with 7x plus 15. And now I'm left with one equation with one variable that I can solve. If I distribute that 10, I get 4x plus 70x plus 150 equals 2. Combine like terms and you get 74 plus 150 equals 2. Subtract 150, divide by 74, and we get the value of our first variable. X is equal to -2. From here, it's the same as what we did with the elimination method. Once you know one variable, you just plug that into either equation to solve for the other variable. So I'm going to take x equals -2, and I'm going to plug it into the top equation. So here's the top equation, I just rewrote it. And now I'm replacing the x with a -2. If I simplify, I end up with y equals 1. So my final answer to this system is -2, 1 if I decide to write it as an ordered pair. Once again, I'm not going to show you out the process of doing this, but it would be worth your time to plug this in as a solution to the first equation and to the second equation to make sure that it works, to make sure it gives you an equation that's true. All right, so this has been my video about how to solve a system with the elimination method and the substitution method, and I talked briefly about which method I would choose for which types of problems. Hope this was helpful. Have a good one.